Hi, how are you? We're now on lecture A2. In the previous lecture, you saw that if you define the sum of two vectors in a very particular way and a scalar multiplication of a vector in a very particular way, the set of all real numbers then becomes a vector space. Today, we look at the set of all real numbers as a metric space. The idea here is that you are in the set of all real numbers and you now want to measure the distance between any 2 points. So when you measure distance, you have to have some way of measuring that distance, which is known as a metric. Definition: the set of all real numbers is called a metric space if you can take any 2 points in the set of real numbers and measure the distance between them, which means you have to be able to come up with a scalar, a number called d. And now a little bit of notation. This is the distance, literally a number, which is measured by some equation between x and y. So this is your distance function. This is a very specific equation that gives you the distance between x and y and spits out a number called the distance. So the set of all real numbers is a metric space. If there's somehow out there somewhere an equation called the distance function that allows you to measure the distance between 2 points x and y. But for something to be a distance function or to act as a distance function, certain things have to be true. The first one is the distance between a point and itself must be equal to 0. So you notice the distance of x and y is 0 when you have x being the same as y. This is intuitive. Next one should be, even it sounds a little bit hokey pokey, but you're about to see that there are some equations that violate this. A legit distance function, a proper way of measuring distances between 2 points, should have this property. The distance between x and y should be the same as the distance between y and x. It doesn't matter which direction you go in, and that distance has to be positive so long as x and y are not the same point. So something like this. Here's x, here's y. The distance from x to y is the same as y to x. And that distance is going to be positive as long as, of course, the 2 points are not the same. Then comes a triangular inequality, which says something along the following lines. It says the distance from x to z plus the distance from z to y. So that triangle x to z, z to y, that total sum must be bigger than or equal to the distance from x to y. So going from x to z and z to y should be a greater than or equal distance from going from x to y. And as a way to sort of understand what's going on, you should ask yourself, why is this expression not with an equal sign? Why is it given as a bigger than or equal to sign? So in which cases will this be equal? In which cases will this be strictly less than equal? If you come up with any equation that has these three properties, we call that equation, that distance function, a metric. Here's some examples. It's really important to know which space you're in. So you'll notice that these are 2 points on the real line, just any two numbers. And now let's measure the two numbers, the distance between the two numbers, as first take the difference between them, square it, and then square root. And I ask you if that's a legit metric, in the sense that does it satisfy all three properties you saw on the previous slide? Now let's go to 2 dimensions. Now you'll see what I've done is I've taken this one-dimensional variation and extend this to 2 dimensions. So now you'll take the first coordinate of x, subtract the first coordinate of y, then square it. Add the second coordinate of x minus the second coordinate of y, square that, take the square root of the whole sum. And again, I ask you, does it satisfy the three properties you saw on the previous slide? The answer, by the way, for example one and example two is yes. These are legit metrics. In fact, if I go from one dimension, two dimensions, three, four, five, six, all the way to n dimensions, this would then be the distance function in n dimensions. If you just extend this, and this is known as the Euclidean distance function, named after, of course, Euclid. You're working Euclidean geometry. So if anyone says, give me the distance according to Euclid's measure, this is what you use. Now let's go to example number three. Once again, you're back to the real line, any two numbers real line, and now the distance between the two of them, any 2 points, you take the difference of those numbers and you take the absolute value. Once again, you're asked, does it satisfy the three properties you saw on the previous slide? Example 4. We're back now in two dimensions, x and y plane. Take any 2 points in the xy plane, two dimensions, and if the points are the same, the distance is 0. If the points are not the same, the distance is always equal to 1. So it's a very funny creature. You're in two dimensions. If I take 2 points which are one and the same, the distance is 0. And if I take 2 points which are not the same, it could be anywhere, right? 1, 1, 10,000 minus infinity, maybe not minus infinity, but 10,000 minus 10 trillion, the distance will be equal to 1. And once again, you should ask yourself, is this equation a valid way of measuring distances? Does it satisfy the three properties you saw on the previous slide? Next up, we are back to the real line. Now somebody says, give me 2 points on the real line, two numbers, and I'll measure the distance between them by taking one number minus 2 times the other number, take the absolute value. And again, you should check if this is a legit metric. You should, the way to do this again is to run through those three properties one by one by one, right? Start with the first one, and you can kind of eyeball and see that right off the bat, the first property is going to break down. Over here, now you're back in two dimensions, xy plane. Take 2 points in the xy plane, and now you measure the distance between them according to this formula. Once again, you should go through those three properties and ask yourself if this is legit. Back to the real line. Now what you do is you measure distances as take one number, square it, subtract the other number squared, take the absolute value. You should see by playing around with each of those three properties that it is in fact not a valid way. It's not a real distance function because it violates at least one of those three properties. But this is because this distance function was the distance between any two numbers on the real line. Remember, the real line goes from minus to plus infinity. What if I said to you that you now are only going to measure distances between any 2 points between 0 and infinity? So you're ruling out negative numbers. Would that be a legit way of measuring distances? Well, you should check it for yourself. Back in two dimensions. And again, you can see that the way to measure distance between 2 points may be that you take the x1 minus x2, which is, remember, is a little bit more devious, right? This is the vector x1's first coordinate, the vector x's second coordinate. Take the absolute value. Take the first coordinate of the y vector, subtract the second coordinate of the y vector, take the absolute value. And is this a legit metric? And again, going back to the real line, now we're measuring distance by taking one number, subtract the other number, and square it. I'm going to give you a hint for this one. Imagine if x was minus 1, y was 1. What would the distance between x and y be? Now imagine y is 1, z is 0. What's the distance between y and z? And of course, that you can use a triangular inequality to see does it actually satisfy the triangle inequality, which is, remember that the distance from x to y plus the distance from y to z must be less than or equal to the distance from x to z. I may have mixed up the x and y's and z's, but the principle is exactly the same. Having given you some examples of distance functions, let's now move on over here. So we're going to use the Euclidean metric, which is you measure distances between 2 points, whether you're in one dimension, two, three, four, five, n dimensions of real numbers, according to this Euclidean formula. In Wolfram Alpha, you can use this command right here to measure the Euclidean distance. So here's an example. There's a vector 1, 1. Here's x, 1, 1. Another vector y, 4, 2. Someone asks you for the distance between x and y. So what you're asking is, what's the distance between the tip of x and the tip of y? If you use Euclidean distance measure, you would use this formula, and then you arrive at the answer square root of 10. We now go to another concept called inner product of two vectors, and from that we see how to measure the length of a vector. The inner product of two vectors, sometimes also known as inner scalar product of two vectors, is you take one vector x, another vector y, and whenever you see the notation x dot y, it's understood that you're looking at the inner product. So the inner product is going to be as follows. Take the first coordinate of x1, multiply with the first coordinate of y1. So take the first coordinate of x, multiply with the first coordinate of y, x1, y1, plus second of x plus second of y. You keep doing this all the way to the nth coordinates. So when you sum all these things up, you get a number, a scalar, right? It can't be more than one number. It's not a vector. And that is known as the inner product of two vectors, x and y. In Wolfram alpha, here's the notation. Notice that you have the dot is down here, and you can get the answer for this exercise right here. What's the inner product of 1, 1 and 4, 2? By hand, if you do it this way, you get the answer 6. You, of course, get the same answer if you do it by Wolfram alpha. There's some rules for inner products. So in this slide, bold x, y, z are vectors. Baby t is a scalar. And so you should really work out every single one of these and convince yourself that these in fact are true. So is it true that the inner product of x and y is the same as y with x? Yes. So go through these things over here, verify each of these rules that you see over here. So once again, inner product of two vectors x and y is defined as this sum that you see here, the scalar. And now we wonder whether we can sort of, if someone says to us, give me the distance between x and y, the Euclidean distance, can I express that in terms of inner products? Yes, you can. Let's say you are in space of all real numbers, n dimensions, and someone gives you two vectors x and y, and asks you to measure the distance between the tip of x, the tip of y in n dimensions. Using the Euclidean distance measure, here's how you would measure the distance between x and y. When you compress this to a summation form, you start to notice something over here. So wait a second, there's a sum here, there's a sum there. Instead of baby x, you have baby x minus y. Instead of baby y, you have baby x minus y. So you notice that if this expression was the inner product of x, if this was the inner product of x and y, then this thing right here, besides square root, should be the product of x minus y, right? And x minus y. So here's the inner product of x minus y with x minus y. When you take the square root of this, you get the distance between x and y. All right. Using what you just saw right now, going back again, if someone says given the distance between x and y, you take the inner product of x minus y with x minus y, and then take the square root. With that, you can measure the length of a vector. By length, what you really mean is, what's the distance of this vector from the tail, starting at 0, all the way to the tip? Well, the notation is this. So you have to know from the context whether we're talking about distances, lengths, or absolute values. So in this context, You know that this is a bold X, and you know from the slide that we're talking about a vector. So this means that this is the notation for the length of a vector, which is the distance of this vector, the tip of this vector X from 0. Applying the formula on the previous slide, it should be the square root of the inner product of x minus 0 with x minus 0. You should now apply those rules of inner products. You can't just go from here to here on an exam. You won't get any points. You kind of have to break this down. So you have to open the bracket, say x dot x minus 0 dot x, etc., etc., etc. Using these rules you saw on a few slides back, you should get this formula, right? Which, of course, if you write it out nicely, boils down to this. So if someone says, give me the length of a vector x, you will take each coordinate of x, right? Because it's an n-dimensional vector. So x1 squared plus x2 squared plus x3 all the way to xn squared. Sum them all up, take the square root. And so if someone says, give me the length of the vector 1, 4, here's exactly what you do. 1 squared plus 4 squared. And when you square root this, square comes out with square root of 17. It is the same answer, by the way, if you use Wolfram alpha. Notice the nomenclature here is length, or the syntax is length space vector, right on the vector. Same answer. There's some rules when it comes to the length of a vector. Once again here, x and y are vectors. Baby t is a number. This says that the length of a vector is strictly positive, except when x is the zero vector, in which case it has zero length. You should vaguely remember this from somewhere. What's the length of a vector multiplied by a number? Well, the absolute value of that number times the length of the vector. This says the length of two vectors added together is less than or equal to the length of the first vector plus the length of the second vector. Once again, this looks mighty familiar, right? This is the Cauchy-Schwarz inequality. Angelo Bellino, who's going to do econometrics for MFEs, is definitely going to do this. You want to be careful. He does not forgive mistakes. It's grad school at U of T. You're no longer in some, you know, that would be true for some third-rate institution, but something like U of T, we don't make mistakes like this. The length of the length of a vector found by the inner product of x and y is less than equal to the length of the vector x multiplied by the length of the vector y. Notice I did not put a dot in between. Right? You don't want to do that, obviously. Right? Um, let's move forward. We now talk about taking a vector y and projecting it onto another vector x, and from that we get something called orthogonal vectors. Sadly, we must do a little bit of baby elementary school geometry. Here's a right angle triangle, 90 degrees over here. Take some angle, theta. Opposite theta is this side right here, O. Adjacent to theta is this side over here, and that's the hypotenuse. The sine of theta is the opposite over the hypotenuse. The cosine of theta is the adjacent side over the hypotenuse. And the tan is the opposite side divided by the adjacent side. It's a very easy way to remember. Sine, opposite over hypotenuse. Oh, as in, oh my God, I got an A plus in my course. Cosine would then be adjacent over hypotenuse. I passed echo 1010. And tan sadly is opposite over adjacent, or which sounds like some Spanish, you know, greeting gone wrong. Maybe they're drunk. Now comes nasty stuff. Very important for econometrics, also important for machine learning. Professor Marlene Coffey has just joined U of T. If you read her papers posted on the Econ website, you can see she uses applications of what you're about to see right now. Here's the story first. Here's a vector x, here's a vector y. What you want to do is you want to drop a perpendicular line from the tip of y onto a line passing through x. That's a mouthful. Once again, imagine you could draw a line through x. This right here, going like this. What you want to do is you want to take the tip of x and you want to draw a line which you want to drop it perpendicular going to the line through x. So you don't want to go like this. You don't want to do this. You don't want to do this. You want to do this, which is dropping a perpendicular. Hits this thing at a right angle. Remember, it's just a pure coincidence that x is over here. Had the tip of x been over here, you would have drawn a line and then hit the perpendicular over here. Now you notice that if you think of going from the origin to this point right here, that's a new vector. Let's call that vector baby t times x. Why? Because it's a number. You can see that it's a shortened version of the original vector x. So it has to be some number multiplied by x. And it's obvious that in this example, that number baby t has to be a number less than 1 because the gray vector here is a shrunken version of the original vector x. Now, this is 90 degrees right here. And now look at this angle theta over here. So you'll notice that when you project a vector y onto the quote-unquote line passing through x, you get a brand new vector called baby t times x. You now want to use this picture, right? And you want to prove this result in general. You want to prove that in general, baby t, what's that multiplicative factor required when you need to multiply x so that you can drop the perpendicular onto the line passing through x, and then you will hit the tip of tx. You should show that is the inner product of x and y divided by the inner product of x and x. Right? So you should prove this. I'll give you a hint. You should remember Pythagoras' rule, a squared plus b squared is equal to c squared. So apply that rule over here. Spend some time, you need lots of coffee and so forth, no sleep. And then ultimately, you should be able to prove this result. And then you want to spend some time here thinking about this picture. This picture, baby t, is a number less than 1 because you can see it is a shrunken version of x. Then you ask yourself, can you draw x's in a different way, the vector x in a different way, so that t is a number bigger than 1? Easy to do. Equal to 1, and less than 1, you've already done this. And then you should also look at the fact, what will actually happen if t is 0? Please remember, the idea that t could be less than 1 includes the fact that it could be between 0 and 1, or it could in fact be negative. So you want to play around quite a bit drawing some pictures to work out all these cases and really grasp the intuition behind t being equal to 0. With this, we now move to the following. Notice that on this picture, I took the tip of y, dropped a perpendicular onto the line passing through x. And it should be kind of fairly obvious that the vectors y and x are not at a right angle to each other. Right? This is not a right angle theta. But here, when I took the tip of y, dropped a perpendicular line through x, I notice that this angle is in fact a right angle. So you start to wonder, there's two ways of thinking about this. One is, when are x and y perpendicular to each other? When are x and y at a right angle to each other? Or when is the case when I drop the perpendicular from the tip of y onto the line passing through x, this angle ends up being the right angle, 90 degrees. Again, I drop a perpendicular from the tip of y through the line passing through x and wonder when this will be a right angle, 90 degrees. You should now be able to easily prove, using that cosine results and sine results we showed earlier, that if x and y are orthogonal to each other, which is a very fancy word for saying they are perpendicular to each other, then the inner product of x and y must always be equal to 0. So once again, if x and y are perpendicular to each other over here, the inner product of x and y must be 0. If x and y are not perpendicular to each other, the inner product of x and y cannot be 0, as you can see by this example right here. Now we go to some really nasty stuff, not pleasant. This is one of those cases, one of the reasons why you're doing math camp is you really want to sharpen your your ability to evaluate statements. So this becomes like a law school exercise. It's very precise in what we say and we don't say. For those of you who are going to take game theory with Martin Osborne or any other professor at U of T, it's a one. The reason those courses are really hard is because they're based on extremely precise mathematical statements. I'm going to speak very slowly. Some people find it annoying, but what can I do? All right. We first want to start with the notion of a neighborhood. Intuitively, you could actually have a point, and let's say R2, and you want to now ask yourself, what's the neighborhood? So all distances here are measured with respect to Euclidean distance function. You're sitting in Rn, and now you choose a point, any point in Rn. So for convenience, you can imagine a certain point right here in R2. In fact, you can see the coordinates are here. Just read down x is equal to 1, y is equal to 2. So what's the neighborhood around 1 and 2? A neighborhood around this point is a set, meaning a collection of points. This set is called N for neighborhood. X means is centered on that point, which down there was 1 and 2. And the epsilon here tells you the the radius of this neighborhood. In what particular sense? Let's start one more time. A neighborhood centered around a point x is a set of points around x consisting of all points y, these are all points y, whose distance from x and y is less than the number epsilon, for some number epsilon bigger than 0. What in God's name does that mean? It means the following. Step 1, give me an x, a point where this neighborhood is going to be centered. In this example, that point is 1 and 2. The next step is to choose an epsilon, any number epsilon. You could choose 1, 2, 5, 1,000, 1 trillion. It just has to be positive. I chose 0.5. And intuitively, what you want to do is a neighborhood consists of all points where the distance between the center, x, and any point is always less than 0.5. So notice that this point right here, this is 0.5, distance 0.5. The distance between this red dot right now and the center of the circle is less than 0.5. The distance between the red point and the center of the circle is less than 0.5. The distance between this red point and the center of the circle is less than 0.5. But if you look at the edge of the circle very carefully, notice that this was a strict inequality, not weak. It says less than, it does not say less than or equal to. And because it says less than, what you're doing is this circle has no solid edge. So in this case, a neighborhood would be as follows. It would be centered on the point 1, 2. It would be a circle around the point 1, 2. right? And that's the equation of the circle. So this is the equation of the circle in R2, such that any point in the circle always is the distance less than zero point 0.5 from its center. So once again, this red dot is less than zero point 0.5 units away from the center. So is this, so is this. But as I get to the exactly the edge, on the edge, that particular point is exactly zero point 0.5 units away from the center. And that point cannot be in the neighborhood. So this dashed edge, anything on the outside of the circle, is not in the neighborhood because it's not less than zero point 0.5 units away from the center. Right? It's in fact exactly zero point 0.5. So this red dot is in the neighborhood. The distance is less than zero point 0.5. This red dot is not in the neighborhood. The distance is not less than zero point 0.5. In fact, it's exactly zero point 0.5. And this red dot is not in the neighborhood because its distance is not less than zero point 0.5. In fact, it's greater than zero point 0.5. So I hope you get the idea that essentially choose a point, give me a radius, and quote unquote draw a circle with no edge. Anything inside that circle, excluding the edge, is the neighborhood centered around that point X. So in this example, you notice that in R2, when I talk about a neighborhood, by this example, you can see it should be an open circle, sometimes also known, by the way, as an open ball. Okay? It's not rocket science to ask what will the neighborhood in 3 dimensions look like. It's obviously going to be a sphere, but no without an edge. And now you ask yourself, what will the neighborhood in 1 dimension look like? So can you imagine what it should be like? So, you should choose a point on the number line. And now you want a neighborhood. So you should define a distance, zero point 0.5 for example, and you should stretch your arms in either direction, but the neighborhood will be all points, stretch your arms out, which is zero point 0.5 units, less than zero point 0.5 units away. So see if you can actually draw or graph that neighborhood. Now comes hell. I'm going to give some definitions. You're not going to get it the first time around. It takes practice. So we have to massage these statements, go over them again and again and again, tweak them to see what they're saying. Let me first read them out. First of all, we already know a neighborhood of a point X is quote unquote an open ball centered around X with a radius of a number less than epsilon, where epsilon is something you choose. Now imagine your space of real numbers. If it's convenient, you can think of the XY plane. Now we imagine a set E. And now we're going to say a few things about this set E. A point X, I never said it's a point that's in E, not in E, but it's just a point X. It's called a limit point of the set E if every neighborhood of this point X contains another point. See, another because it says y must not be equal to x, so that the other point is in the set E. So you draw a set E and you wonder whether a point x is a limit point of that set E. What you want to do is you want to see if every neighborhood danger statement, which means no matter how small that circle is or big, the open ball can be very small, medium, large. Every open ball around that point X must contain another point Y that belongs to the set E. If that is true, then that point X is a limit point. Otherwise, it isn't. Now, what about the set E? The set E is going to be called a closed set if every limit point is a member of that set. This is really, really hard. You first ask if any given point X is a limit point of the set E. As you're about to see, it doesn't guarantee that the point X is a member of E. It could be outside of E. Now you're asking a different question. Is the set E closed? it is going to be closed if every limit point that you identified is a member of that set. Now look at something else. A point X is an interior point of this set E if you can draw an open circle around this point X so that the neighborhood is entirely within the set E. Once again, you want to know if X is an interior point of the set E. You draw a neighborhood. If you can find at least one neighborhood, a neighborhood, so that the neighborhood is completely inside the set E, that's an interior point. So I hope you started to notice some subtle differences. Here, every neighborhood, here is a neighborhood. And now the set E is going to be called open if every point of E is an interior point of E. So if every member of the set E is an interior point of E. Let's start. Examples. This is nasty, 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 nasty. Let's first find out how to identify limit points. So what you've done is you can see that I've drawn a circle of quote unquote radius 1 centered around 0, 0. So you can see that here's 0, here's 0. It's a circle of length 1 because you can see from the equation. But the set E not only consists of the circle centered around 0, 0 of radius 1, excluding the edge, but it also, that's a sign for union, it also consists of the point 2, 0. So the set E consists of the circle, excluding the edge, and the point 2, 0. I wonder what the limit points are. So you could start anywhere. Let's pick this one right here. Is this a limit point? It would be a limit point if, you should read the definition again, if every neighborhood of this point contains another point that's a member of E. So let's start. Let me draw a circle. Does this circle contain a point that's a member of the set E? The set E, by the way, is the one that's shaded blue plus a blue point. Well, no. You can see this red dot is not a member of the set E. So there's no way it can be a limit point because it had to be true for every neighborhood. So I found a violation for one neighborhood. There's no way this can be a limit point. What about this one right here? Well, every neighborhood, every circle that I draw here has to contain another point, but there's a member of the set E. I've drawn a circle. You can see this red dot is not in the set E, which is again the shaded blue area and the blue dot. So again, this cannot be a limit point. What about this point right here? Is it true that every circle that I draw, no matter how small, no matter how big, every circle that I draw around that point, centered around this point, does it contain at least one point that's in the set E? And the answer is yes. You will notice that no matter how tiny the circle, no matter how big the circle, you can even draw it like this, is going to contain at least one point that's in the set E. So this is a limit point of the set E. What about a point that's sitting on the edge itself? Remember the edge is dashed. The set E does not contain the edge. But what about this point that's on the edge literally? Is it true that every circle that I draw contains at least one point that's in the set E? Yes, it is true. I can draw a tiny circle. Imagine there's a tiny circle. And even though these are not points that's in the set E, here are some points that are in the set E. So I can draw a tiny circle, and no matter how tiny the circle is, I'll always include some points that are in the set E. At least one point is in the set E. So that means it's a limit point. So I have identified all the limit points of the set E. Limit points of the set E are all the points on the circle of this region right here and inside the circle. Interior points. A point, any point X is an interior point if you can draw a circle around it so that the circle is entirely within the set E. Once again, let's go here. What about this point right here? Is this an interior point? Can I find at least one neighborhood that is entirely within the set E? If you've forgotten, the set E here is again the same blue circle, excluding the edges and the blue point. Can you find me one circle centered around this point that is entirely inside that set E? Well, no. There's no way, no matter how tiny the circle, no matter how large the circle, no circle will be entirely inside the set E. So that's not an interior point. What about this one? Can I find at least one neighborhood, any neighborhood, tiny, big, that is entirely within the set E? No. In this circle, you can already see this is not inside the set E. If I made the circle tinier, again, that circle would not lie entirely within set E. If I made the circle larger, not true. What about this point inside? I just have to find one neighborhood. So don't be going, so take this point, imagine the sentence right here. Let's not go drawing huge circles right now. Because for it to be an interior point, I just have to find one circle that has to be inside the set E. So you can see that I found one circle that in fact is entirely inside the set E. So this is in fact an interior point. So you might start noticing that this point is not only an interior point, but it's also a limit point. And what about a point that's on the edge? I know from the previous slide it's a limit point, but is it an interior point? Well, no, because no matter which neighborhood I try to draw, big, small, large, whatever have you, there is no way the circle is going to be entirely within the set E. So we know that's not an interior point. So what are the only interior points of the set E? It's all those points on the circle, excluding the edge. All right? Now, is a set closed or is a set open? Life sucks. These are the definitions for your convenience of limit points and interior points. This is real, very precise, and you have to read the logic. A set E, the set E, is going to be called closed if every limit point of that set is a member of that set. Now imagine that the set E is this gray circle, including the hard edge over here. Okay? That's a set E. Cool? What are the limit points? Well, what about this red dot right here? That's not a limit point because not every neighborhood centered around this dot is going to capture at least one point in the set E. Well, you should realize, I mean, you pretty much, it's pretty obvious. Any point inside the circle is an interior point. Any point on the circle is also any point inside the circle is a limit point of the set E. Any point that's on the edge of the circle is also a limit point of the set E. Now, are all the limit points members of set E? Yes, right? For example, so every limit point that you found, whether it was inside the circle or on the circle, was in fact a member of the set E. So it is in fact a closed set. In contrast, you have the circle here, but now you have no edge. Again, I know this point right here, the yellowish one, is in fact a limit point. Again, I know that this point on the edge itself is also a limit point. Anything outside the circle is not a limit point. So what are the only limit points of the set E? All things in the gray shaded area, excluding the edge, and all points on the edge are limit points. But are all limit points members of the set E? No. These limit points is a member of set E, but those limit points on the circle itself are not members of E. Therefore, it's not a closed set. You need to first, so the procedure, if you actually want to think of it this way, first find out all the limit points. Then ask, are all the limit points also members of set E? If they are, it's a closed set. What about an open set? The set E is going to be called open if every member of that set is an interior point. Ooh, different. In the previous slide, I first identified limit points, then asked if all those limit points are members of the set E. Now I do something different. Now I ask if every member of the set is also an interior point. So here's a circle with a hard edge. Are all the members of the set interior points? So the procedure is a little bit different now. Let's pick a point inside the circle. Is this an interior point? Yes, it is. Now we look at a point on the edge of the circle. Why? Because that's a member of the set. Is that an interior point? Interior point. Well, no, because you don't have a neighborhood that's entirely inside the set. So notice that some members of set E are interior points, while other members of set E are not interior points. Therefore, there is no way the set can be open. Again, you now have a new set E that's this gray area excluding the edge. We know this is an interior point, that's inside circle. We know that's not an interior point. Is it true that all members of the set E are interior points? Well, yes. Anything in this gray disk, excluding the edge, is in fact an interior point, right? So this is an open set. Whereas over here, anything on the disk and the edge, right? Some of those were interior points, while others were not interior points. That's why this was not an open set. Here, every member of the set, the gray disk, excluding the edge, is in fact an interior point. Therefore, this is an open set. And now something even more cunning. A gray disk. It excludes the edge over here, excludes, no edge. But then there is an edge here. See how there's a line segment here? So let's see. Is every member of this set an interior point? Let's start with this member. Is this member of the set on the gray disk itself here an interior point? Yes, it is. It's this point. I don't need to consider this because it's not in the set, so I don't even need to bother looking at this. I do need to look at this point because it's a member of set E, and also if it's an interior point. But no, it's not, because when I draw, there's no ball, no neighborhood that is entirely contained inside the set E. Therefore, it's not an open set, and it's not a closed set either, because you can see this is limit point, that's a limit point, that's a limit point. But the limit points are not members of the set. Right? So I hope you appreciate what the procedure was. So to find out what the closed sets are, first find out all the limit points. And ask if all the limit points are also members of the set. In this case, that is true. This is a closed set. To find open sets, only look at those points which are members of the set and ask if the interior points. I did. Some of those members of E are interior points, while other members of E are not interior points. That's why it's not an open set. Now we look at bounded sets. A bounded set says a set E is bounded if you can find a number so that the distance of every point in E from the origin, remember how you calculate distances? Distance is always measured from the quote-unquote, from the tip of the arrow, which in this case, there's no arrows here, but from the point and the origin. So a set is bounded if you can find some number so that the distance of any point, every point in that set from the origin is at most this number k, in plain English. Is it true? Here's the origin. You might notice that Square brackets here, square brackets. Everyone knows, of course, I know that what this means. It means that this is the interval here. The set E is all numbers from -1 to 100, including the numbers -1 and 100. Here, it's all numbers from -1 to 100, including -1, excluding 100. And these are all numbers from 1 to infinity, including 1, and of course, infinity goes on forever, like true love. Let's see if this is bounded. Here's the number 0. Is there any number, can you name any one number so that the maximum distance of any point from the origin is less than that number? So my good friend here next to me uh, is a little drunk. He says, yes, the number 20 works. Sadly, my friend is wrong because there are points whose distance from the origin is more than 20. But what if you said 120? So k is 120. Well, you can see that every point in a set, their distance from the origin is less than the number 120. Therefore, this set is bounded. This set is also bounded because, let's say if I chose the number k 120, the maximum distance of any point from the origin is less than 120. Again, a bounded set. That's not a bounded set because if I named 120, I can still find points which are more than 120 units away from the origin, right? Because this goes all the way to infinity. That's not a bounded set. This is a bounded set. This set is centered on 0, 0. Name a number. You can see the radius of the circle uh, is 2, right? So give me any number bigger than 2. Let's say 3. So this is a bounded set because the distance of any point from the origin is less than the number 3. Bounded set. That's not a bounded set because here's 0, 0, where the red dot is right now. And the set only consists of all xy combinations which are less than or equal to the number 1. So now you ask yourself, is this bounded? Well, no, give me any number k. Let's say k is 120. So the question now is there any point that's less than 120 units away from the origin? Well, no, because notice how 2k0 is the number, right? So here's 2k is x. So 2 times 120 is 240. And 0 is y is 0. So 240 is number less than, 240 is, x and y is, let me just 1 second make sure. Let's see. X and y is, sorry, let me just, something having a little wipe out here. Let's see. So you have taken a number k. That's right. So you can see that, right? So take any point that's actually 2k. So pick a number k. Now consider 2k and 0, which means it would be somewhere around in this direction, right? Right here. And remember, this region goes and approaches the x-axis asymptotically like this, right? So 2k would then be over here somewhere, and that would be a number that's greater than k, right? And still within this set over here. Okay, so again, it's helpful to draw it out like this and see what happens, right? So, and you can see that in fact this would not be a bounded set. If that didn't make sense to you, take the number 2. So now consider the number 2 times 2, 4. So 4 will be somewhere around here. So you can see 4, 0 is a number whose distance is greater than k. It's 2 units away from 0. Again, not bounded. Okay, so here's a summary. We already know when a set is closed. We already know when a set is open. We already know when a set is bounded. If a set is both closed and bounded, we say that set is a compact set. We do some exercises. We're going to go through these examples right here and see what happens. it's very important to see which space these sets are in. So you wonder, is the set between A and B sitting in R1? The set A and B is sitting in R1, which means it's a line segment which includes the number A, includes the number B. You wonder if it's closed, open, bounded. Let's start. So to help you, choose a number for A, let's say 2. Choose any number for B, let's say 10. So you now have an interval that's, set E consists of all points between 2 and 10, including the number 2 and including the number 10. So now the question is, are there, let me try to change this. Is this a closed set, open, bounded? First thing you need to do is find out all the limit points. So is this a limit point? No, because it's not the case that every neighborhood contains a member of the set E. Is this, sorry, you know what? I shouldn't have done that. My bad. Sorry. Let's erase this for a second. Let's start one more time. Is this point a limit point? Because you're working in R1, your neighborhoods are no longer looking like open balls. They're going to look like these intervals, right? So you imagine you're stretching your arms out. So you have a line segment, but excluding the endpoints. It's starting to look like Star Wars shit. Anyway, so that's not a limit point because it doesn't include any. So if I stretch my arms to the left or right, no matter how wide I draw the interval or how narrow, it's not the case that every neighborhood ends up capturing a member of the set E. What about over here? If I stretch my arms out, so here's a center. If I stretch my arms out in any direction of any length, will I end up capturing at least one point that's in the set E? And the answer is yes. I'm going to stop doing this because obviously I have really horrible artistic skills, but you can see that no matter, you always, so these, any points between 2 and 10 are limit points. What about this one? 2. Yes, as I draw any neighborhood, you can see that I'm going to draw neighborhoods of now bigger. No matter which neighborhood I draw, I always end up capturing at least one point that's sitting in E. So what are the limit points of this set? The limit points of the set are all the points 2, all the points between 2 and 10, and including 2 and 10. So the entire interval. Are those limit points 2, 10, and anything in between also members of the set E? Yes, they are. So it's a closed set. For an open set, I had to ask the question, is every member of the set an interior point? So let's go back to the point again. Let's do a highlighter this time. Let's take a point right here. Is this an interior point? Yes, it is. I have been able to find a neighborhood that's completely inside the set. What about this one? Is that an interior point? Well, no, because I can't find a neighborhood that's entirely within the set. So some members of set E are interior points, such as the number 8. Other members of set E are not interior points, such as the endpoints. So since not every member of the set E is an interior point, it's not an open set. And is it bounded? Yes, because every point in the set lies less than, let's say, I don't know, 100 units away from the origin. So it's closed, open, and bounded. Now we go to a different example. Same as the last slide almost, but this time excluding the points. Once again, the same exercise. To find out if it's closed, take a point outside. Is this a limit point? Well, no, because no matter what neighborhood I draw, I'm never able to, not for every neighborhood, it's not true that I can capture at least one point in set E. What about these points? Anything between 2 and 10. Those are limit points because for every neighborhood I draw, I'm able to capture at least one point that's in the set. So we know that anything between 2 and 10 is a limit point. What about the endpoints themselves? Yes, those are also limit points because I can, for every neighborhood I draw around the number 10, no matter how, right, I'm going to go up here just so that you can see, no matter how wide the neighborhood, is always going to capture at least one member of the set E. Therefore, the limit points are anything between 2 and 10, and the endpoints 2 and 10 as well. But are all limit points members of the set E? Well, no. The endpoints 2 and 10, those are limit points, but they're not members of the set E. Therefore, the set is not closed. Is it open? Well, yes, because every member of the set is an interior point. So it does right because no matter which point I take, I'm always able to find a neighborhood that's strictly within the set. Some of you might say, well, what about if I get really close to this? Well, if I get really close to number 10, remember, you're not hitting the number 10. So you can always pick any number as close as possible to 10. So take any number as close as possible to 10, 9.99999999999999999. Then look at the distance from 10, divide by 2, and that neighborhood would be strictly contained within this interval. So the set is open. And is it bounded? Yes, it's pretty obvious it's bounded because, anyway, you get the point. Now we're trickier. Let me go back to the pointer. So here's what's happening is you're now again considering a line segment where you don't, but now instead of being R1, you're now saying R2. So the trick right now is that your neighborhoods are no longer line segments, but rather open balls. Right? So your set E is this line segment in R2, excluding the endpoints. And now the question is this a closed set? To do this, I first find out, I first find out all the limit points. Is this a limit point? Well, no, because not every neighborhood around this point captures at least one point in the set. Is this a limit point? Yes, every neighborhood that I draw will give me at least one point that's in the set. So anything on the blue line is a limit point. Are the endpoints limit points? Yes, because no matter what circle I draw, how big or small, I'm always going to capture at least one point as in the set. So the limit points are the endpoints, which in this case would be 0 and 1, 10 and 1, and anything on the line segment between. But not all limit points are members of the set. Anything on the blue line is in the set, the endpoints are not in the set, therefore the set is not closed. What about open? Now things get tricky. So it looks a bit deceptive. You may be tempted to say, wait a second, pick this point. Now draw a neighborhood. Some of you might say, you know what, well, it looks like the neighborhood is inside the set. But you're falling into a trap because the set is only along the blue line. So when you draw a neighborhood, only these points right here are in the set E. Those right here are not in the set E. So you can see that anything on the blue line is not an interior point. The endpoints are also not interior points for the same reason that I can't find a neighborhood. It's impossible to draw a neighborhood where the neighborhood is completely inside the set. So therefore, it's neither open. Pretty nice. Is it bounded? Yes, because you can define some number, some circle of some radius, right, where the entire set is always going to be within that radius. This is now the set of all integers. Lexicographic orderings 0, 0, 0, 1, 1, 1, 1, 2, all integers right here. So the question now is it closed? This is going to be very dangerous. So far, the way you've argued whether something is open or closed is in the case of closed, you first had to identify limit points and then ask, is every limit point a member of the set E? Let's see. So let's find the limit points. Is this a limit point? No, because not every neighborhood, this is an R2 by the way, not every neighborhood of is going to capture member E. Is this a limit point? No, because not every neighborhood, here's one neighborhood that does not capture members of at least one member of E. I mean, this neighborhood does, but not that neighborhood right there. So that's not a limit point. Nothing between these dots is a limit point, and there's nothing else left. I can't find any limit points. So without having any limit points to check for, I can't confirm the statement whether it's a closed set is vacuously true because the definition was a set is closed if every limit point is a point E. I can't see, I, 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 I haven't been able to identify limit points over here. And because of that, this statement then becomes vacuously true. So set becomes closed because since you haven't seen any limit points, right? You haven't been able to, you can't then, so because of that, uh, the statement then becomes vacuously true. Um, what about open? Open means is the case that every member of the set is an interior point. So I don't need to look at points in between. Those are not members of the set. Excuse me. I only need to look at points, excuse me, that are members of the set. Let's pick this one. Is it true that I can find a neighborhood that contains is contains all members that are strictly inside the set E? But the set E, remember, goes on forever. It's all dots, right? So there's no way for me, even if I drew this circle, I can't do this. I could draw this circle. I do end up including some members of E, but not all members of E. These circles have to be pure subsets of the, the E. So you can see that some of these circles contain members that are not in E, while they contain some members that are in E. Therefore, that's not, I can't find interior points. That's not an interior point, right? And therefore, the set is not, sorry, that's not an interior point. So therefore, uh, not all points of the set are interior points. That's why this set is not open. So in case you're getting confused, there's a subtle difference between the two things. In the case of closed, I first had to find limit points, then ask if they're members. Since I wasn't able to find limit points, the statement then becomes vacuously true. In the case of open, it goes the other way around. I look at all members of points in the set E and then ask if the interior points. So I am able to look at points in E and I'm able to establish that they're not interior points, which means that they're not open. It's not an open set. Is it bounded? No, because since this goes on forever, there's no way that you can draw a circle that completely encompasses the set of all integers. And finally, the worst one of them all, this is a sequence of numbers taken in R2. Notice how n goes from 1, 2, 3, so forth. So the x coordinate is 1 over n, the y coordinate is 1. Here's a y coordinate like this, here's 1. When n is equal to 1, I get 1, 1 as the point. When n is equal to 2, I get half 1, 1/3 1. So you can see the sequence of dots are getting closer and closer and closer, and it's starting to approach here. First question, closed. Well, is this point right here a limit point? But no, not every neighborhood around this point has an element of E, a member of E. So those are not limit points. What about this one? But no, not every neighborhood includes at least one blue dot. What about this one right here? Well, that's not a limit point because not every neighborhood contains at least one blue dot. You can see that if I drew a circle of radius less than 1/2, I would not be able to capture members of E. What about this one? Again, I can always take the distance between this dot and the next one, divide by 2, and draw a circle. So generations of students have gotten confused because they think that a point really close to this 0, 1 here is a limit point. So you can imagine a dot that's really close, and they think that's a limit point, but that's not true because there is some distance between whichever dot you draw close to this one. There's always a distance between that and the dot. You can always take that radius, divide by 2, and that would not be a limit point. What about the number 0, 1 itself? Well, that in fact is again not a limit point because this is where people get really confused. So let's exaggerate the picture a little bit. Here is your point 0, 1. Okay, so I'm just going to sorry, it's not the world's best picture. Here's a point that's really close, right? The sequence is getting closer and closer and closer. But remember, there's always a dot here. I can always find a neighborhood that does not contain any uh, at least one dot, right? So uh, sorry, I take that back. My bad, guys. So this point is in fact a limit point because every neighborhood I draw, so any neighborhood I actually have over here, so like this, any neighborhood that I draw will always contain at least one member of the set E, at least one blue dot, right? Because these blue dots are getting closer and closer and closer and closer and closer and closer together to the number 1. See how these things are very devious? So there's all between any dot, there's another dot, there's another dot. So you'll always be able to find every neighborhood that you draw will always have at least one dot inside. So this is in fact a limit point. But the problem now is it a closed set? For it to be a closed set, I need to ask, are all limit points members of the set? There's only one limit point, 0, 1, and 0, 1 is not a member of the set. Remember that despite the appearances, those blue dots, even though it looks like they're converging, they don't actually end up hitting 0, 1. And for that reason, since there is a limit point, 0, 1, since 0, 1 is not a member of the set, it's not a closed set. Is it an open set? Is it true that there is a neighborhood around every member that is includes all members of the set? Well, no, because here are the members of the set. Here's a open ball that I've drawn so far that does not contain all blue dots right here. Therefore, it is not open as well. It is bounded because everything here lies within quote unquote a circle of some number. You can just choose a really large number like a 100, and therefore it is actually bounded. Right? So now we summarize. So here's a summary, and you should be able to see how it's compact, depending, of course, whether the sets are closed and they are bounded. Thank you very